Addition Polymers Simplified. Now we begin by some definitions here. Polymerization is a process in which large molecules, which are called polymers, are made by linking many small molecules that are called monomers. We give you some additional information here about polymers. That polymers that consist of identical monomers are called homopolymers, while those that consist of two or more different monomers are called heteropolymers or simply copolymers. Now, as we also know, polymers may be natural or biopolymers or man-made, where man-made polymers are also called synthetic polymers or plastics. Now, we have two types of polymerization. We have addition and condensation. Now, addition polymers are formed when monomers simply add onto a growing chain as intact molecules. When it comes to condensation polymers, these are formed when monomers combine, but then there is elimination of small molecules like those of water. This video is meant to simplify addition polymers. We welcome you as we promise to do another video where we shall simplify the condensation polymers. So let's now take a journey through the addition polymers that we learn in Organic Chemistry 2 at Form 4. The first addition polymer we present is polyethylene or simply polythene. So let us have a look at its monomer. Its monomer is a thin molecule with the structure C double bond C and 4 hydrogen atoms, ethene. So how do we represent the polymerization process? We need N molecules of our own monomer, where N here means many or millions of these molecules. So we subject them to high temperature and high pressure, and we end up forming a long chain of polymer. Remember, the double bond would be broken, and then now we have an endless chain. So this is our monomer, ethene. This becomes the representation of the polymer polyethylene. One thing that a candidate should do or should know is that we started with 2 carbon atoms in our monomer. The polymer should have multiples of 2 in the bracket here. We don't allow numbers that are not multiples of 2. So if a candidate would maybe draw a structure that has 3 carbons inside the bracket, that is not acceptable. Let's look at the uses of polyethylene. We have making packaging bags. We have making flexible or squeeze bottles, making toys, and making of insulation material for electric cables. Our second addition polymer is polychloroethane, or what is commonly called polyvinyl chloride. The monomer is simply chloroethane or what is commonly called vinyl chloride. So vinyl chloride has the structure C double bond C. We have hydrogen atoms, but then there's a chloride atoms in one of the carbons. That becomes chloroethene. Now, the polymerization process involves combining N molecules of our monomer to form our polymer. So here we are, representation of the polymerization process. We'll have this kind of an arrangement. Again, the polymer should have number of carbons that are multiples of your monomer. That becomes the representation. So moving to uses, we have making of plastic pipes, we have making gutter pipes. All these are owed to polychloroethene. Car dashboards, protective clothing, floor tiles, and even hose pipes. The third addition polymer is polypropene. The monomer is simply prop-1-ene or propene. Now, we will draw our monomer with the last CH3 like I've just drawn, so that it comes out clearly when we do the polymerization. So we don't make this to look like a straight chain, but like a bended alkene with the name prop-1-ene. When it comes to representation of polymerization process, we need millions of our monomer molecules, and we end up having our polymer that will have this kind of an arrangement in the structure. Quite easy to do. You break the double bond and the chain becomes endless. So there we are. Now, polypropene is used in making plastic crates. We also get plastic chairs out of it, and even plastic bottles. The fourth addition polymer we present is polyphenylethine, which is known out there as polystyrene. The monomer is phenylethine. Now, phenylethine can be represented in two different ways. We have the phenyl group that can have C6H5 as the structure, or we can actually draw the phenyl group as a cyclic hydrocarbon. So we'll have it here, cyclic hydrocarbon here. This is called the phenyl group. This one here, C6H5. And here we have 5 hydrogens that are linked to 6 carbon atoms in a circular manner. That is the phenyl group. So coming to polymerization process, N molecules of our monomer combining to form our polymer. So here we are, polymer coming out from million molecules of the monomer. Quite easy to do. From polyphenylethine or from polystyrene, we make heat insulation materials. We also make ceiling tiles, which are also called ceiling lines. Our fifth polymer in the category of addition polymers is polytetrafluoroethene. The monomer is tetrafluoroethene that has the formula C double bond C, and we have fluorine atoms attached to the two carbon atoms as indicated here. To representation of polymerization, N monomers or N moles of monomers being reacted or being joined to give a long chain. Sorry for this. Give a long chain that would look like this: Polytetrafluoroethine. Now this has the following uses. First, we use polytetrafluoroethine to make the non-stick coating, which is usually found in cooking pans, cooking pots, or underneath or below the iron boxes, of course electric iron boxes. We also use polytetrafluoroethine to make what we call greaseless bearings. These are used in moving machine components. Now to our sixth addition polymer with so many names: Perspex or polymethyl methacrylate or polymethyl methylpropenoate, plexiglass or lucite. All these names are for the same material, and it is a very common substance used as glass. It has properties of glass, if not better, because it is unbreakable but transparent. Let's now look at its monomer. The monomer has the following structure: C double bond C, CH3, C double O, CH3, and then we have H and another H on the first carbon. To learn how to name this monomer learners, let us consider a familiar organic substance with almost a similar structure. So let us look at this. Suppose I have C single bond C, then C double O CH3, then I have H, another H, then the other carbon with all the three H's. If we look at this structure, it is almost similar to what we have here as our monomer. So when we learn how to name this, we shall then be able to know the name of our monomer. Now this second structure here is actually an alkyl alkanoate. It is an ester. So how do we name esters? In class, we told you we start with the carbon or the number of carbons that are after the double O. So because we only have one carbon after the two oxygen atoms here, this becomes a methyl for the alkyl group. And then for the alkanoate group, we shall go for the number of carbon atoms before the double oxygen atoms. And we can see there are three. So our name becomes methyl propanoate. One carbon after the double O and three carbons before the double O. Having named our second structure, allow me now to introduce the branch CH3 on carbon number 2. And then we also learn how to name our new structure. So we shall have C. There are 3 hydrogens, just as we have in structure 2. And then I'm now creating a branch of methyl group on my carbon 2. so that I have a structure that is almost similar to my monomer. So for our third structure, the name is almost similar to the second one, but we have to take care of this branch. This is a branch that we call methyl, and it is on carbon number 2 if we count from the left hand side. As usual, we begin with naming the branch. So my branch is a methyl group on carbon number 2. So I have 2-methyl here, and then the name will be similar to the one I have for structure 2. So this would be 2-methyl and then methyl propanoate. That becomes the name if I introduce a branch on carbon 2. Now if you look at our monomer, it is exactly the same as my structure 3, only that we are introducing a double bond, and then now one hydrogen will have to be let go for carbon 1, and this other one for carbon 2 will also be let go. So then this is now exactly the same as our monomer. Now because of the double bond, the name will now change from propanoate here to propenoate, because now we have a double bond. Learners, I have taken you through a journey of how to name our monomer. So finally we can agree that the monomer for our polymer perspex is actually 2-methyl. Then we have a structure that looks like an ester but has a double bond that we call methyl propenoate. That becomes the name for our monomer, 2-methyl methyl propenoate, which others call methyl methacrylate. Having learned how to name our monomer, let's now have a look at the representation of the polymerization process. So we have n moles of our monomer, forming a very long chain that will finally give us our polymer. So here we have n moles of our monomer giving us an endless chain that we call perspex. So here we are. That becomes our polymerization process representation. Good enough. Now, perspex is used as glass. So anything that glass can do, perspex can do better. So we have making aircraft windows, making watch glasses, making contact lenses, including drinking glasses or any other thing that glass can be made of. Our seventh polymer we want to discuss is natural rubber with the name Polyisoprene. The monomer is 2-methyl but 1,3-diene, which we call isoprene. Now it has the following structure: CH2 double bond C, CH3, CH double bond CH2. So if you look at this, this is a diene made of 4 carbons. The double bond is between carbon 1 and carbon 3. So it is a but 1,3-diene, and of course there's a branch on carbon number 2, which now gives us the 2-methyl as the branch. Now let's look at the representation of polymerization process. Of course I need n molecules of my monomer. Here we are. And I get now my polymer. Of course, I'll be able to break some double bonds to allow for the continuous chain to continue. So this would be my polymer by the name natural rubber or Polyisoprene. Let us talk about this material. We are told it's usually very soft. We need to harden it before it is used. So this hardening process, as we discussed in class, is called vulcanization, where we heat it with sulfur. Now, after it has been vulcanized, can we still draw its structure? Quite easy. So we have our polymer here. If you heat it with sulfur, this double bond would be broken, and then we now allow sulfur atoms to get into the structure to do the vulcanization. So here we shall have our new structure that would now represent what we call vulcanized rubber. So our double bond at this point will now be broken and the chain will continue, but we shall have two pairs of electrons at these two positions that can be used for bonding when I break this bond. So this is now where sulfur atoms get in. So we shall draw maybe two of them here. It's a continuous chain. So after these sulfur atoms have been infused into the structure, we can have another molecule of our polymer continuing with the chain. So this would now be the formula for vulcanized rubber. And I believe you can see how it works very easily from this point when you break the double bond. Two uses of natural rubber: making tires, of course, after vulcanization, making hose pipes, making shoes, valves, and even floor tiles. Lastly, let us look at rubber that is synthesized in the lab. The monomer for our synthetic rubber is just similar to that of natural rubber. The monomer now becomes 2-chloro-but-1,3-diene. Remember, for the natural rubber, the monomer was 2-methyl. So instead of the methyl group, we replace it with a chloro group. And then now we are able to obtain now our synthetic rubber. The monomer would have now this structure, CH2 double bond C, but this time round, instead of CH3 on carbon number 2, we'll have chlorine. Then we continue with almost a similar structure for the monomer. So there we are. Again, this is a diene that has 4 carbons, double bond between carbon 1 and carbon 3, and a branch of chloro on carbon number 2. So the name now becomes 2-chloro-but-1,3-diene. How do we represent the polymerization process? Polymerization process, we shall have N molecules as usual of our monomer, and we obtain our polymer, of course with bonds broken at some points. So this would be CH2C, Cl, double bond now comes there, CH and CH2 with N molecules of that. Now, our synthetic rubber is still used to make tires. This kind of rubber is resistant to attack by petroleum products. So if you need hose pipes for oil and gas, this is the material to go for. We also use it to make electrical insulation materials, seat belts, and gaskets for engines. We finally look at advantages and disadvantages of synthetic polymers as we end this video on addition polymers. So some of the advantages of synthetic polymers are that they are cheaper as compared to the natural counterparts. We also have plastics being resistant to attacks by acids or alkalis, even microorganisms and even pests. So we can conclude that they therefore become more durable because these are agents that we keep on interacting with almost on a daily basis. To the disadvantages now, the main one being that these materials are non-biodegradable, so they contribute to pollution of the environment. Number two, they are highly flammable, and as they are burnt, they produce toxic fumes. With that, dear candidate, we have come to the end of this short video where we have taken a journey with you through the addition polymers that are usually discussed in Form 4. Join us in the next video where we shall take a similar journey through condensation polymers. As usual, we continue to thank you for your following, and we also take this opportunity to wish you all the best in your endeavors.